Let's continue with section 12.8, static equilibrium. An object is in static equilibrium if the net force on it is zero and the net torque is zero. So we can say the conditions for static equilibrium are as follows. 1, the net force is zero, and 2, the net torque is zero. So if those two conditions are satisfied, an object will be in static equilibrium. So net force means the sum of all forces, and net torque also means the sum of all torques on the object. And so we can write the conditions as follows. So we want the x component of the force to be equal to 0. So the sum of all x components to be 0, and the sum of all y components to be 0. And the net torque applies the same way, so the net torque should be 0. Let's illustrate this with an example from your textbook. This is example 12.14 in your textbook. So in this example, we are supposed to find the net force, or find the force on a tendon of the arm. And the diagram is as follows. I will not write the whole exercise out because this exercise is already in your textbook. This is basically exercise 12.14 in the textbook. This is the third edition of your textbook, Knight, Field and Jones, third edition. So in this example, we have the arm represented this way with a hinge, and we have a force this way. This is the force from the tendon which connects to the upper arm. This is the elbow, so we can say this is the force at the elbow, and then we have a force from a mass that is being carried. This mass is a barbell. In this exercise, the known quantities are given to us, and the known quantities are the distance of the tendon is given by 4 centimeters. This is the distance here between the tendon and the arm. This is D tendon. And then the distance of the arm, or the length of the arm, is this distance here. So D arm is equal to 35 centimeters. And the force from the barbell is 450 newtons. So we want to find F tendon. So we first start off by knowing that at equilibrium, the net force is equal to 0. And so we can say that the net force on this object in the y direction, because we are working, the forces are all pointing in the y direction, will be given by the force from the tendon, which is the positive force, minus the force from the elbow, minus the force from the barbell. These forces should all add up to 0, because we said the net force should be 0. And then we also said the net torque should be equal to 0. And so the net torque is equal to the torque, which is the distance from the tendon, multiplied by the force from the tendon, minus the distance from the arm, or the length of the arm, multiplied by the force of the barbell acting on the arm. This should be equal to 0. We've already established that. So if you look at it, then you will see that at the point where the arm is connected to the elbow, since that is the hinge location, the force, the distance of the force, there is no distance between the elbow and that hinge, and therefore the torque there is 0. So the torques are due to the force from the barbell acting downwards and the tendon pulling upwards. And those would tend to rotate in 2 different directions about the hinge. So the force from the tendon would tend to rotate the arm upwards in a counterclockwise direction, and the force from the barbell would tend to rotate the arm downwards in a clockwise direction. So we've already established our convention. We know that the clockwise torque is the negative torque and the counterclockwise is the positive torque. So we can say that the distance from the tendon to the force from the tendon should be equal to the distance, or the length of the arm, multiplied by the force from the barbell. So these are the torques acting on the arm. Note that we have ignored the weight of the arm since it's so much smaller than the weight of the barbell. So from that, the force due to the tendon can be found by just taking the length of the arm, the force of the barbell, and dividing that by the distance of the tendon to the force from the tendon. So we can write that as 450 times 35 centimeters divided by 4 centimeters. In this case, there is no need to change the distances to meters because the distances, the centimeters cancel out. So the force from the tendon is just equal to 3,900 newtons from the calculation. So that's all we need. So if you just do all these calculations, if you want to know the net force, if you put this 3,900 newtons in the first formula we found for net force, they should all add up to equal 0. So this allows us to find the force on the elbow, but we don't need to find that now. So if we wanted to find it, we could calculate it. Well, why not do that also? The force net is just equal to 0, and that should be equal to F tendon minus F elbow minus F barbell. And so F elbow would be equal to F tendon minus F barbell. So if you like, we can find that force. So the F elbow is equal to 3,900 newtons minus 450 newtons, and that should be 3,450 newtons. So that's just a quick example on how to use the net force and the net torque to calculate forces in static equilibrium. There are other examples that you can look at in the textbook yourself. So let's go on to the next section. I'm going to go on to section 12.10, the vector description of rotational motion. So in this section, we shall use our understanding of the vector cross product to identify the direction of the torque in rotational motion. So if you have an object like that in a plane, let's say we have two vectors. Let's call this vector A and vector B. So let's say this is vector A and this is vector B. And the angle between the vectors is an angle, let's say, phi. So the cross product of these two vectors is another vector C. Let me write that the cross product of vector A and vector B is a third vector C, given by C equals A cross B. The direction of the vector C is a direction perpendicular to the plane of A and B. So we can illustrate that as below. So we have our object again. So this is vector A and that's vector B, and the angle between them is phi. So the cross product is a vector C that is perpendicular to the plane of the two vectors. This is similar to what we did for torque. So in our definition of torque, we had two vectors. So we had a vector which was the lever arm R, and a third and another vector which was the force F, and the angle between them was phi. We could write this way, where this is the lever arm R and this is the force F, and the angle between them is phi. So the torque is a vector that points perpendicular to the plane of those two vectors. So we can write torque to be equal to R cross F, which can be written as R F sine phi, where phi is the angle between the two vectors. And if we want to be more formal, then we can say that these two vectors, we are talking of their magnitudes now. So tau is the magnitude of the torque.